Hello, we are Group 2, Team GMI, Great Mind Incorporation. Our team members is Awan Izzuddin, Anis, Fikri, Farah, and me, Fahda. For the integrated project, the question requires us to prepare a piping line from product streams of distillation column to the storage tank. Both streams need to include a pump unit. Besides that, need to identify the type of pipe, the diameter, the fitting, and the connection of the stream. We come up with this design where we have 2 distillation unit, 3 cooling unit, 3 pump unit, and 3 storage tank.
In this section, I will explain about the type and material that we choose for the storage tank and its justifications. So firstly, the type of storage tank that we choose is internal floating roof tank. The material that we use for the storage tank is stainless steel because it offers a great resistance to corrosion, heat resistant, is cost effective, and also durable.
In this design condenser unit, 5 units of 90-degree long elbow fittings, 3 check valve, 3 cooling unit, 3 pump unit, also 3 storage tank to store benzene, toluene, and xylene respectively. So the material used for the tank is stainless steel to avoid corrosion from occur. The type of storage tank is internal floating tank. The diameter and height of tank is referred from the reference, which is 39 meter and 20.7 meter respectively. The height of maximum level liquid that can be stored into this tank is 20 meter. Therefore, from the diameter and height of tank, we can obtain the volume of tank, which is around 24,739 meter cube. And the capacity storage for the liquid is 15,898.95 meter cube, which is enough to use for mass production.
Some advantages of using this type of tank, including the abilities to reduce the evaporation loss from 80% to 90% due to the separation of the air and the liquid when the liquid floats up or down on the roof. The separation of liquid and air also helps in avoiding hazards such as fire or explosions. The volatilization loss from the liquid can also be further reduced due to its fixed roof and gas phase layer between the fixed roof and the internal floating plate that helps in heat insulation. Accumulation of rain or snow can also be avoided, so we can save more accessories such as ladder or central drain that will help in maintaining the tanks more easily. Due to the reduced oscillation of liquid in the process of conveying liquid in the tank, also, we can reduce corrosion and thus increasing service life. Lastly, there will also be small breathing loss since there are less amount of liquid that will be lost due to the liquid vapor and the air induction.
For my part, I will be explaining on the calculation of pressure drop and pump power. It is to store 3 product streams to their respective tanks. Without further ado, let's start with the first product streams. It is connecting product streams M2 and tank number 8. Using Bernoulli equation, we're going to find for the pump work, and then from the pump work, we're going to find the pump power. According to the assumptions, we can cancel out a few terms in the Bernoulli equation. First, large surface area of tank at the relative velocity V at approximately 0 meter per second. Secondly, datum at point 8 saw Z at equals to 0 meter. Thirdly, no work turbine involved. Fourth, pump efficiency is 90%. Lastly, at pump elevation and friction is negligible. After we cancel out all the terms, then rearranging the equation, we found the formula to find pump work of this stream M2. Work pump 2 equals to pressure drop of 0.8 N2 over the density of the stream, plus with the total friction loss of pipeline 2, minus with V squared over 2, minus with gravitational acceleration times with Z2. To find the velocity V2, we use the formula of volumetric flow rate Q equals to area of pipe A times with velocity V2. Making V the subject, V2 equals to Q2 over A, but we only have the mass flow rate M dot. Calculating Q using the M dot over rho, we find the Q2 equals to 0.21917 meter cube per second. Area of pipe A equals to pi over 4 times the inner diameter, which is 0.26471 meter, we got A equals to 0.055101 meter square. Back to finding the V2 equals to Q2 over A. We got V2 as 3.977750 meter per second. Next, in Bernoulli equation, we have to define the Z2, which is elevation from the inlet of tank to the vertical height of the condenser. Here, we define Z2 equals to 7.5 meter. Before we have a look at the total friction loss of pipeline 2, F2, let's see the calculation for pressure drop of point 8 from point 2. Using the formula from NASA website on finding the total pressure, P total equals to static pressure rho GH plus with dynamic pressure rho V squared over 2 for both P8 and P2. Rearranging the equation, we got total P8 minus total P2. Moving the density to the left-hand side, we find the pressure drop over density of P8 from P2 as negative 76.581248 joule per kilogram. Now, we look at the calculation for the total friction loss of pipeline 2, F2. The formula used is F2 total equals to the summation of friction loss in pipe plus friction loss in fittings plus friction loss in valves plus friction loss due to expansion plus friction loss due to contraction. The first one, F pipe. We are using stainless steel pipe size 10, inner diameter of 0.264871 meter with surface roughness of 2 times 10 to the power of negative 6 meter. The length of the pipe 2, as in the sculpt diagram, is 132.5 meter. We use the formula to find F pipe equals to 4 times friction factor times length of pipe divided by diameter times with V squared over 2. For friction factor, we determine the flow as turbulent flow by checking the Reynolds number, rho V d over mu. Mu is the dynamic viscosity of benzene at 20 degrees Celsius. Next, we use the turbulent formula for finding friction factor. Small f equals to 2.6526 times 10 to the power of negative 3. From there, we substitute all the value we find into the F pipe equation. We found that F pipe equals to 5.307784 V squared over 2 joule per kilogram. For F fittings, we consider if we are using 90-degree long radius elbow with quantity of 2, we find the fittings as 0.92 V squared over 2 joule per kilogram. For F valves, we used one check valve, so F valve equals to 2 V squared over 2. For F expansion, considering slightly rounded case, K factor of expansion is 1, so the F expansion equals to 1 V squared over 2 joule per kilogram. For F contraction, considering slight rounded case, K factor of contraction is 0.2, so the F expansion equals to 0.2 V squared over 2. Completing all 5 values affecting total friction loss, we substitute back into the value of the equation on the top left over here with the same V2, which is 3.977750 meter per second. We find the F2 total is 74.585533 joule per kilogram. So, we have find all the value for the equation of work pump. We substitute all, we find that WP2 equals to 83.481962 joule per kilogram. Calculating for the power of pump 2 equals to m dot times power work pump ideal calculated just now divided by the pump efficiency. Mass flow rate 2 is 192 kg per second. Pump efficiency is 0.9. We find the power of pump 2 equals to 70,809.49 watt. For the next one, stream number 4, we use all the same formulas to calculate work pump. pump power, and the pressure drop of 0.7 from 0.4. Stream 4 is mainly 98% tall-wind, so we use approximation ρ 4 equals to ρ of tall-wind. Mass flow rate of 300 kg per second, we find V4 as 6.27 at 452 meter per second, Z4 as 6 meter, pressure drop over density as negative 78.56994 at 0 joule per kilogram. F total for calculation, length of pipe is 122 meter, the same pipe, the same number of fittings, and same valve as well as the same case for expansion and contraction. We found that F total for equals to 172.293 at 6 joule per kilogram. Using the rearranged Bernoulli equation, we find the WP4 as 15.154926 joule per kilogram. Calculating for pump power efficiency with efficiency 0.9, the pump power of 4 is 5051.64 watt. So, we do the same steps for the last stream number 5. Using m.5 is 508 kg per second, we find V5 as 10.670060 meter per second, Z5 is 1.5 meter, pressure drop over density is negative 66.735090 joule per kilogram. F total 5 calculation is length of pipe is 115 meter, the same pipe, the same number of fittings and valve as well as is 444.842313 joule per kilogram. Using the rearranged Bernoulli equation, we found the WP5 as 306.467133 joule per kilogram. Calculating for the pump power with efficiency 0.9, the pump power of 5 is 172,983.67 watt.
In this system, the child valve is used as it can prevent the flow back towards the distillation column. Then the condenser is used in condensing the vapor of the fluid used into the liquid so it can flow through the pipeline system towards the storage tank. After that, the efficiency of the pump is assumed to be 90% as this is the common efficiency for the pump use so the liquid can be transferred efficiently. And then the stainless steel pipe is used because it is the corrosion resistance, can stand with various of temperature, either high or low temperature, and it is resistant to the UV radiation. After that, the cooling unit is also used to reduce the temperature of the fluid as it is higher in the distillation column than in the pipeline system. Furthermore, the fitting used is 90-degree long elbow as the flow must be changed in direction according to the system. Then the friction loss and elevation of the pump for this system are considered to be 0. Furthermore, the velocity for all the tanks is also be 0 since the tanks are too large. After that, the datum for it is like Z6, Z7, Z8 is 0 as the initial elevation is measured from the inlet to the level of the outlet stream of distillation unit. The distance of located tank with distillation unit is more than 100 meter as it is the safest distance and can reduce the risk of damage if the explosion of tank or distillation column occurs. Then the work of turbine is 0 joule as the system doesn't use any turbine. Roll fall is assumed to be roll tall wind as it has measured amount around 98% in the stream, whereas the roll 5 is a rule for xylene as stream 5 has 98% of xylene and it's considered to be the large amount.